Today's talk, I will be covering the basic concepts of environmental technology. An overview of environmental technology includes the principles, planning, design, construction, and operation of the following systems: drinking water treatment and distribution, sewage disposal and water pollution control, stormwater drainage and control, solid and hazardous waste management, air and noise pollution control, and general sanitary community conditions. In the world of environmental technology, it's pretty much the application of the concepts that are derived from either policies that come from public health protection or from environmental health measures. The public health protection component is involved with the prevention of the transmission of diseases among human beings, whereas the environmental health component involves preserving the quality of our natural surroundings, including water, land, air, vegetation, and wildlife. Often, both of these disciplines are intertwined and sometimes called for one or the other. The public health component is not just the absence of illness, but it deals with the holistic health of the individuals and communities that are subject to public health measures. As what we see today in current times, where we have a pandemic where we need to implement public health measures such as the wearing of masks, social distancing, and personal hygiene. These things are the basic necessities needed to protect the public, and also there's a need to protect the environment as well, because many times we find that the environmental factors exaggerate health conditions such as what we find in the current COVID-19 pandemic situation with respiratory distress. So sanitation is a key component of environmental technology. Within environmental technology, there are professionals that work and are labeled a number of things, but in general, some of them are called sanitary engineers, public health engineers, pollution control engineers, or environmental health engineers. And within this group, there are different levels of specificity, if you want to use that term. The engineers are typically at the highest rank, or in a sense more rigorous in their educational background. The next level would be the technologists, and then there's a typical entry-level technicians that are found in the field of environmental technology. Overall, environmental technology is an interdisciplinary field because it encompasses several different technical subjects. There are a number of different subjects that an environmental technology person can specialize in, and there's no one path to take, such as for my own background, I have a degree in mathematics and physical science, and then I picked up another degree in a more specific field called environmental toxicology, and later on I ultimately have picked up a graduate degree in environmental engineering. So some of the basic subdisciplines of civil engineering lay the foundation for much of what we find in environmental technology. And those topics are hydraulics and hydrology, biology, ecology, geology, chemistry, and a variety of different specialties, which makes this field of environmental technology exciting and sometimes very complex, but challenging field to deal with real-world problems. In the field of environmental technology, there's a number of different ways you can approach this subject matter, but the way I approach it, overall learning, is that you would have a concept that you have theoretically have learned about and done extensive studying on, and then there is the relationship to the mechanics. And when I say the mechanics, it's the taking of the conceptual vision of something and then transferring it into some type of mechanical formula relationship where you can introduce some type of quantitative approach to, or it doesn't have to be quantitative. It could be just some type of relationship consideration between items, and then ultimately taking the next step where you would find an application to the initial concept that has an application to it. But in order to bridge the gap between the concept and the application, you must have the basic fundamentals and the mechanics to draw some relationship between the concept and the application. In the world that we live in the modern civilized, so-called civilized world that we see around us, it's a built-up world where humans have taken a concept, taking the next step of finding some type of mechanics to take the concept and then find an application. Now, sometimes the application drives the need for the concept, or the concept drives the need, ultimately will develop an application. And a lot of times in the world of, I guess, academics, you would say that there are the theoretical types that study physics, and pure mathematics, or the philosopher types that are looking at social issues, and they are more into the theories of economics, for instance. But in a sense, some of these folks might not even be looking for an application. And in some areas of education, they pretty much don't want to, or try to stay away from the applied component, where the applied folks, which are typically engineers, have a basic fundamental understanding of the concepts of, in this world, we deal with the technical, scientific knowledge of physics, chemistry, biology, geology, atmospheric science, fluid dynamics, you name it, and then looking at the real world, either creating something from the knowledge base through some type of mechanics where you would find a mathematical relationship between some items where it will ultimately create a output, which will be an application. I think to make things a little more entertaining, a good film to watch, other than its high drama, is the film Chinatown, which was directed by Roman Polanski, which is also an interesting person, and starring Jack Nicholson and Faye Dunaway, and a variety of other actors from the early 70s. And in a nutshell, this film was a Hollywood dramatization of the real world development that had occurred in Southern California, and how Los Angeles ultimately was developed into what you see today. Now, at that time of the period of development would be the early 20th century, which would be about 1900 to the 40s, and there was a shortage of water. And one of the things that humans need, not only for their own biological purposes, but also for industry and for folks overall to have proper sanitation, the utilization of clean, potable water is essential for a successful and possibly efficient society. So as the city of Los Angeles, the city and county of Los Angeles was developing, a number of questions were posed, such as, is there an existing public water system with the capacity to connect with and serve the new developments in the city of Los Angeles? Is it best to build a new centralized treatment and distribution system for the whole city? Or would it be better to use individual well supplies, such as groundwater? Is there a need for centralized water treatment? What types of water treatment processes will be required to meet the federal, state drinking water standards? And what would be the optimum hydraulic design of the storage, pumping, and distribution network to ensure that sufficient quantities of water can be delivered to customers in Los Angeles at adequate pressures? And because of the problems associated with the development of Southern California, a special note, the California legislature developed restrictions on new developments because of the lack of fresh potable water supplies. Okay, once you develop all of your water supply, now you need to run it through the processes of the factories, the cities, the irrigation, and also the households and buildings and schools. Raw sewage needs to be discharged, typically through sewage conveyance systems to a wastewater treatment plant. Again, if you were developing a new community, you would try to determine if there's any municipal sewage systems that can handle the new waste load. And then you will also need to look at the geological conditions for situations where you may be able to dispose of the wastewater subsurface, and that's typically for rural residential properties that are on septic. Again, you would have to look at the level of wastewater treatment that needs to be done. There's different levels of wastewater treatment. Will there be a need of primary, secondary, and possibly even tertiary wastewater treatment? You also will have to understand that there is also industrial wastewater, and that industrial wastewater from factories, automobile shops, welding shops that have boilers, hot temperature, plating shops, paint shops, hospitals, a variety of different industrial sites have to discharge their liquid waste to a treatment system. Typically, they would pre-treat and discharge to a sanitary sewer system, or they ultimately, if a sanitary sewer system is not available, they would, in a sense, develop their own wastewater treatment plant and get their own wastewater permit to discharge, and that is known as the MPDS permit. Also, if the industrial facility is going to develop their own waste treatment system, how would that system be designed, and is there restricted land space and use that may require a higher level of technology to treat the wastewater. Ultimately, when you do treatment of wastewater, you would have some solid waste, such as sludge, that needs to be disposed of, in addition to the liquid waste. And ultimately, we'll look at the optimum layout and hydraulic design of the sewage collection system that will convey the liquid waste efficiently to a centralized wastewater treatment plant. Another component of environmental technology is stormwater management. Now, there's a number of things that are of concern where you deal with stormwater. Typically, stormwater is what surface water that is originating from precipitation of rain, and that precipitation undergoes a process of flowing to creeks, rivers, lakes, and to oceans. But the process of stormwater management in general has two areas. One is flood control, and two is appropriate management of potential potable drinking water. Again, things to consider are: what is the optimum layout and hydraulic design of a surface drainage system that will prevent local flooding during wet weather periods? How would the intensity and duration of storms affect the design of the system without surcharging or overflowing? Are there local restrictions on construction site management or development of where the runoff from storms has to be maintained as development occurs, as if no development occurs? Perfect example is if you install a parking lot where they had a grassland, the permeability of the parking lot is much lower than the grassland. Therefore, the stormwater will rapidly find its way flowing off of the pavement and into other areas where normally that stormwater would have percolated into the soil and had ample time to commingle with other storm streams, rivers, tributaries, to find its way naturally to the lakes, rivers, and bays and oceans. Another key item involved in stormwater management is best management practices for reducing peak runoff flows and to protect water quality during wet weather periods. Another note would be, since we're here in California, the scarcity of fresh potable water the rainwater is subject to a lot of restrictions on pollution in the form of chemicals and even sedimentation from construction sites. So, as mentioned before, it's a fine balance between the flood situations and maintaining the quality of the water for potential potable use downstream. Another key area of environmental technology is solid and hazardous waste management. Solid waste is basically our garbage that we accumulate mainly due to our consumerism, where we have things packaged or we have things that are made that become disposable. And ultimately, the items that we have will have to find their way to a landfill. And of those items, we have material that can go to a landfill and either biodegrade or, in a sense, be recycled potentially prior to going to a landfill, or have inert properties where if they go to a landfill, they'll stay there without finding themselves migrating out into groundwater or being part of a pollution issue. So, solid and hazardous waste are part of waste management. Proper handling of waste is a key part of public health and environmental health, where we would prevent the spread of disease such as typhoid and plague and the breeding of rats and flies. Improperly disposed of solid waste can find its way into the groundwater table by leaching. The leaching would be either chemical or biological, where the chemical leachate would find its way into the groundwater table, and the biological organic material can produce microorganisms that will find itself into surface water, which in some situations would be found in drinking water also. Other wastes that are known as hazardous are typically poisonous or ignitable or reactive, that pose a public health threat and also environmental degradation effects on wildlife. Perfect example is improperly used pesticides that find themselves in a waste container, or in a sense polluted or released into the environment, causing environmental harm to wildlife, such as the substance known as DDT. So, as a part of environmental technology, landfills are engineered. They're engineered just like buildings are engineered, where they have controls to prevent leaching of substances into groundwater or gaseous substances being released into the environment. In some situations, the gases are captured and energy is generated from substances such as methane gas produced from organic biodegradation. So, in addition to clean water supply and wastewater disposal, a new development such as what you have seen today in Los Angeles has to have some type of landfill. Or one of the key things to realize is that landfills fill up and they ultimately will close. So you need to divert waste material into a recycling stream if possible, so we can lessen the burden on the landfills that we have. Landfill placement and construction, specifically the location of a landfill, and also wastewater treatment plants, are difficult to site in today's constrained urban environments and even in rural environments, due to the deleterious effects of odor, of smells, and of the materials that are placed into landfills, and the process of delivering waste to a landfill and the associated trash that may fall off the trucks into the neighboring communities draw a negative view upon such facilities. So the development of a area such as Los Angeles in today's world may be impossible due to all the constraints and the term NIMBY, not in my backyard. Another area of environmental technology involves air and noise pollution control. So, in much of what we see today, we use fossil fuels to power the automobiles, to run generators for electricity, and to heat facilities for heating, and also for just a variety of different things. And these processes generate air pollution. And a lot of the industrial facilities also produce sound, which, when it's loud enough, becomes a nuisance, or also known as noise pollution. California, especially Los Angeles, had undergone so much development. So by the mid 1940s, the 50s, the 60s, the amount of development in production and use of fossil fuels exploded exponentially to where you would have air emissions that were equivalent to burning of black soot in the air. So Los Angeles and the Los Angeles Air Basin was one of the first in the nation to develop regulations to control air pollution. And that's where you have the development of agencies such as the South Coast Air Pollution Control Districts, and even in the San Francisco Bay Area, the Bay Area Air Quality Management District. So we also have this effect of development, from finding clean water to getting rid of the clean water that becomes a waste, either as an industrial liquid waste or a sanitary solid waste. And then you would have the hazardous wastes that are developed from materials that are used in industries and even residential and other types of industries will develop hazardous waste. And then we get to the air pollution, which has its waste in itself, but both mobile sources such as automobiles and trucks and trains and airplanes and ships, as well as stationary factory sources, which have stacks that emit plumes of smoke. So by the time of the turn of the 1960s and the development of the environmental movement, of major publications and such as Silent Spring by Rachel Carson, we find the government, both the local and state and federal, starting to develop regulations to either control or eliminate pollution. And much of this has brought on the fields of environmental technology, which typically is dealing with the problem after the fact, and the problem is pollution. But at times there are ways to prevent the pollution from happening initially, and a lot of that has to do with doing an environmental impact statement and laws and regulations at the federal level, state level, and even the local levels to evaluate the impact of development on communities and communities' public health as well as their environmental health.